A corroded bronze lump found in a shipwreck holds the world's first computer. We are taught to see ancient history as a time of myth and simple tools, but that story is incomplete. This exploration will uncover ancient tools that reveal a scientific mindset far ahead of their time. By the end, you will gain a new lens to see human ingenuity, one that transforms the past from a static record into a living source of inspiration. How did a 2,000-year-old device predict eclipses with clockwork gears? What was the purpose of a clay jar that could generate electricity? These are not anomalies, but evidence. They prove that the drive to measure, to experiment, and to understand is a timeless part of who we are. What does true innovation look like when it is stripped of all our modern advantages? That corroded bronze lump from the Aegean Sea did not emerge from a vacuum. It was born from a specific way of seeing the world, a mindset that modern labels often struggle to contain. To truly appreciate these ancient tools, we first need to dismantle a common assumption: the idea that science is a purely modern invention confined to white lab coats and sterile environments. In antiquity, the pursuit of knowledge was not a separate discipline. It was a seamless part of philosophy, art, engineering, and even spiritual understanding. The goal was not just to know how things worked, but to understand humanity's place within a vast, interconnected cosmos. This was a holistic science, one that saw patterns in the movement of stars, the growth of plants, and the principles of leverage, all as expressions of a single, underlying order. Think of a master sculptor in ancient Greece, tasked with creating a monumental statue. A modern artist might focus on form and expression, but that ancient artisan needed to be a geologist and an engineer as well. He would carefully select a block of marble, understanding its grain and internal stress points to prevent it from shattering. His tools were extensions of precise physical principles, levers and wedges that multiplied force in predictable ways. His work was both an artistic triumph and a practical application of material science. This is the essence of the ancient scientific mindset: empirical observation married to deep, purposeful inquiry. Historians like James Burke have highlighted how these early thinkers were pattern seekers. They watched the dependable cycles of the heavens, the predictable flooding of rivers, and the consistent behavior of materials under stress. From these observations, they began to form testable hypotheses, the very seed of the scientific method. Could they predict an eclipse based on past cycles? Could they design an aqueduct that used gravity alone to transport water for miles with a precise, gentle slope? Their drive was for repeatable, verifiable results, a quest for precision that transcended the immediate task. It was this foundational attitude, valuing meticulous measurement, logical deduction, and elegant problem-solving, that set the stage for objects of breathtaking complexity. With this lens in place, we can now turn to our first artifact, a device so anachronistic its discovery was initially met with disbelief. The storm that sank that ship around 100 years before the Common Era did more than just claim a vessel. It created a perfect time capsule, preserving a secret in the dark, cold silence of the Aegean Sea for 2,000 years. In 1901, sponge divers exploring the wreck near the island of Antikythera brought up a lump of corroded bronze and wood, its original form completely obscured by centuries of mineral crust. To the archaeologists of the time, it was a curious oddity, perhaps a piece of a statue or a navigational instrument, and it was largely set aside. The true nature of this object, now known as the Antikythera Mechanism, remained hidden for decades, waiting for technology to catch up to its ancient genius. It was not until the mid-20th century, with the advent of X-ray and later advanced three-dimensional imaging, that the lump began to reveal its secrets. Inside was a breathtakingly complex assembly of at least 30 interlocking bronze gears, precisely machined and mounted within a wooden frame about the size of a shoebox. This was no simple calendar. It was a mechanical model of the universe. By turning a hand crank on the side, an ancient user could advance the device through time. As they did, dials on the front and back would move, displaying the positions of the sun and moon against the backdrop of the zodiac, predicting lunar phases, and even forecasting solar and lunar eclipses with remarkable accuracy. One dial tracked the 4-year cycle of the Panhellenic Games, including the Olympics, tying celestial time to human cultural events. The engineering precision is staggering. Some of the gears have teeth cut at precise angles, and one gear features a pin and slot mechanism that elegantly models the elliptical, variable speed orbit of the moon, a subtlety of astronomy that was not formally described until Johannes Kepler in the 17th century. This device represents a fusion of deep astronomical observation, advanced mathematical calculation, and masterful miniaturized engineering. It proves that a group of Greek thinkers had not only mapped the cycles of the heavens, but had also mastered the art of translating those abstract cycles into tangible, moving metal. The Antikythera Mechanism forces a profound question. We are accustomed to a linear story of progress, where complex technology arrives in the modern era after a long dark age. But here is an artifact that shatters that timeline. Its very existence implies a tradition, a school of thought and craftsmanship capable of producing it. Who made it? For whom was it intended? A temple, a royal court, or a philosopher's library? And most hauntingly, if this one device survived only by the sheer accident of a shipwreck, how many other marvels of equal or greater sophistication were created, used, admired, and ultimately lost, leaving no trace for history to find? This single artifact redefines our entire perception of ancient technological capability. The gears of the Antikythera Mechanism represent a pinnacle of mechanical prediction, but another discovery points to a different kind of ancient experiment, one involving a silent, invisible force. In the basement of the National Museum of Iraq in Baghdad, there rests a simple clay jar, unassuming at first glance. It stands about the height of a hand, sealed at the top with a plug of asphalt. Inside, however, lies a configuration that has baffled and fascinated historians for decades. A rolled copper cylinder houses an iron rod kept separate by that asphalt stopper. This artifact, dated to the Parthian period around 200 years before the Common Era, is not a storage vessel. When filled with an acidic liquid, something common like vinegar or grape juice, it functions as a basic galvanic cell. The acidic solution acts as an electrolyte, allowing a chemical reaction between the two dissimilar metals, the copper and the iron, which generates a small but measurable electric current. What could this current have been used for? The most compelling theory is electroplating. A Parthian artisan could have used the device to apply a thin, decorative layer of gold or silver onto a less precious metal object, like a statue or a piece of jewelry. By connecting the object to one terminal and a piece of gold to the other, and immersing them in a special solution, the electric current would slowly transfer molecules of gold onto the surface. This is not wild speculation. Modern experimenters have successfully used replicas of the Baghdad jar to do exactly that, producing a fine, even plating. Other possibilities include a medicinal application, where the mild tingling sensation from the current was used for therapeutic purposes, perhaps to soothe muscle pain, a practice that echoes in some forms of modern therapy. Whether for adornment or wellness, the implication is profound. It suggests a culture that was not merely observing nature, but actively probing it, testing combinations of materials to produce a consistent, repeatable effect. This was proto-science in its most hands-on form, a deliberate attempt to harness a natural chemical process in a controlled way, centuries before Alessandro Volta would stack his discs of metal to create the first recognized modern battery. This artifact sparks a question that hums like the current it might have produced. How isolated was this knowledge? The Parthian Empire sat at the crossroads of ancient trade, a nexus linking the Mediterranean world with Persia, India, and China. Could the principle of this simple battery have traveled along the Silk Road, shared between traders, scholars, and craftsmen? Or was it an independent discovery, born from the universal human curiosity to tinker and test? The Baghdad Battery stands as a quiet testament to a practical, experimental mindset, one that sought utility in the subtle dance between metals and acids. It reminds us that the spark of discovery can ignite in the most humble of workshops, not just in grand libraries, and it leads us to consider another ancient tool, one that required no moving parts or chemical reactions, but instead demanded a mastery of perspective and light so advanced it would not be matched for over 1,000 years. While the Baghdad Battery harnessed a chemical reaction, another artifact from the same region sought to command a different fundamental force, light itself. In the ruins of the ancient Assyrian palace at Nimrud, archaeologists unearthed a small disk of rock crystal, carefully ground and polished around 3,000 years ago. At first glance, it could be mistaken for a simple decorative ornament, perhaps an inlay for furniture or jewelry, but its form tells a more intriguing story. The crystal is not flat, it has been shaped into a slightly oval form, a convex lens. When held to the light, it focuses rays to a point, capable of magnifying small objects or, if angled toward the sun, concentrating enough heat to ignite tinder. This is the Nimrud Lens. The debate about its primary purpose continues. Was it a decorative piece, a tool for starting fires, or something far more profound? Given what we know of the Assyrians, the latter possibilities are compelling. This was a civilization of meticulous record keepers, their vast libraries filled with thousands of clay tablets inscribed with tiny, precise cuneiform script. A master scribe or scholar, straining their eyes over such detailed work, might have used this lens as a simple magnifier. Furthermore, the Assyrians were accomplished astronomers, charting the movements of planets and stars with remarkable accuracy for their time. Could a lens like this have been employed to sharpen the view of the night sky, to better distinguish one star from another in a dense cluster? Whether for reading the minute marks of human language or scanning the vast canvas of the heavens, the principle is the same. The Nimrud Lens represents a conscious, crafted effort to extend the natural limits of human sight. It is a physical manifestation of a desire to see more, to perceive detail that the naked eye alone could not resolve. This act of shaping crystal to bend light is a foundational step in the long journey of inquiry. It transforms passive looking into active observation. Every scientist who later peered through a telescope to map the craters of the moon, or through a microscope to discover a world of microorganisms, was following in this same intellectual tradition, one that began with a simple, polished stone in an Assyrian palace. The lens did not just magnify objects, it magnified human understanding, proving that the tools of discovery can be elegant in their simplicity. This pursuit of clarity, of bringing the distant and the tiny into sharp focus, connects directly to our next exploration, a tool that required no magnification at all, but instead demanded a genius for understanding the Earth itself on a monumental scale. The polished crystal of the Nimrud Lens brought the world into sharper focus, but what happens when the Earth itself presents a puzzle that seems to defy all focus, a mystery locked inside a stone? In February 1961, 3 men searching for geodes near the town of Olancha, California, cracked open what they thought was a promising specimen. Inside the hollow rock, instead of the expected crystals, they found a hard, ceramic cylinder with a metal core, all encased in a crumbling shell of hardened clay. To their eyes, it looked unmistakably like a 20th century spark plug. The enigma, soon dubbed the Coso artifact, was born. Here was a manufactured object, seemingly identical to parts from early automobiles, found sealed inside a geode that geological analysis initially suggested was over 500,000 years old. The implications, if true, would have been staggering, a piece of modern technology from a time when early humans were just beginning to use simple stone tools. The story ignited a firestorm of speculation, becoming a cornerstone for theories of ancient astronauts, lost advanced civilizations, or inexplicable time slips. It was the ultimate out-of-place artifact, an OOP art, a term for objects that appear too advanced for their purported time or location. And that is precisely where its true value lies, not as proof of the impossible, but as a perfect case study in the scientific mindset. The mystery of the Coso artifact did not linger in the realm of pure speculation for long. It triggered a rigorous investigation, a collaborative effort between geologists, materials scientists, historians, and even collectors of vintage automotive parts. They applied the very tools of inquiry we have been tracing, meticulous observation and logical deduction. Experts examined the object's composition, its design, and the nature of the encasing material. They compared it to known artifacts from the early 20th century. The critical breakthrough came from a simple but powerful act of cross-referencing. The specific design of the ceramic insulator and the metal components matched spark plugs manufactured by the Champion Company in the 1920s, plugs commonly used in Ford Model T engines and early mining equipment. The so-called geode was not a natural formation 500,000 years old, but a concretion of hardened rust and clay that had built up around the lost spark plug in the damp soil over just a few decades. The investigation was a masterclass in debunking, but more importantly, it was a demonstration of the scientific method in action. A curious anomaly was identified, hypotheses were formed, evidence was gathered from multiple disciplines, and a conclusion was reached based on the preponderance of facts. The Coso artifact story, therefore, is not a failure of ancient mystery, but a triumph of modern analytical thinking. It underscores a crucial point about the mindset we are exploring. The drive to investigate the unexplained is not about blindly believing in wonders. It is about having the courage to ask questions and the discipline to seek answers through reason and evidence. This relentless curiosity, coupled with a systematic process for separating signal from noise, is itself one of humanity's most powerful tools. It allows us to look past the initial shock of the anomalous and understand the real, often more fascinating, story behind it. And sometimes the most profound stories are not told by small, intricate objects, but by the silent, monumental marks we leave upon the landscape itself. The silent testimony of stone can be more eloquent than any written record. High in the Peruvian Andes, the fortress of Sacsayhuaman rises above the city of Cusco, its walls composed of limestone blocks so enormous that their very presence defies immediate understanding. Some weigh over 100 tons, equivalent to a herd of elephants, yet they are not crude, piled slabs. Each stone is a unique, irregular polygon, its faces cut with a precision that borders on the impossible. The joints between these colossal pieces are so tight, so perfectly fitted, that for centuries people have said you cannot slip a razor blade or even a piece of paper into the seams. This is not merely skilled craftsmanship, it is a radical reimagining of architecture itself. The Inca builders, working without iron tools, the wheel, or even mortar, achieved a feat of engineering that modern analysis reveals as profoundly scientific. They were not just stacking rocks, they were solving a complex, three-dimensional puzzle of structural physics. Each irregular shape was carefully calculated to interlock with its neighbors, creating a wall where the weight is distributed evenly across countless points of contact. This design is not just about stability, it is about dynamic resilience. The Andes are one of the most seismically active regions on Earth. A rigid, mortared wall would crack and collapse under the shearing forces of an earthquake. But the interlocking Inca stones have a built-in flexibility. They can shift and settle during a tremor, then settle back into place without collapsing. The builders understood their material and their environment on a fundamental level. They selected specific types of stone for their compressive strength. They shaped them to exploit natural angles of repose, and they designed the entire structure as a single, cohesive entity. This was applied science on a monumental scale. It was a full-scale, physical model of geometric and geological principles, built through generations of observation, experimentation, and refined technique. The walls of Sacsayhuaman and the terraces of Machu Picchu are not just buildings, they are crystallized knowledge, a systematic, problem-solving approach translated directly into enduring stone. From these massive, earth-bound puzzles, we shift our gaze to the opposite end of the scale, to an artifact of delicate and bewildering precision that seems to defy the very capabilities of its era. The massive, interlocked stones of Sacsayhuaman demonstrate a mastery of earthly forces. But what happens when your path lies not across solid land, but across the trackless, shifting sea? For the Norse explorers who ventured into the North Atlantic over 1,000 years ago, navigation was a matter of survival under a perpetually gray sky. Their sagas speak of a mysterious tool, a solarstein or sunstone, said to reveal the sun's position even when it was completely hidden behind clouds or below the horizon during the long twilight. For centuries, this was dismissed as poetic myth, a magical artifact of legend. Modern research, however, suggests it was a brilliant application of physics, using a simple crystal to see the invisible. The key candidate is a transparent mineral known as Iceland spar, a form of calcite with a remarkable property. It polarizes light. Sunlight scattered through the atmosphere becomes polarized, meaning its light waves vibrate in a specific direction relative to the sun's position. To our eyes, this is completely undetectable, but when you look through a crystal of Iceland spar and rotate it, the image you see splits into a double image due to its birefringence. The trick is to find the orientation where these two images match in brightness. At that precise angle, the crystal is aligned with the polarization pattern in the sky, pointing directly toward the hidden sun. Imagine a Viking navigator on the deck of a longship, the world a uniform dome of thick cloud, no shadows, no visible horizon. He holds up his sunstone, a piece of clear calcite, and slowly turns it, peering through. He is not looking for the sun itself. He is looking for a subtle, consistent change in the light passing through the crystal. When the twin images fuse into one uniform glow, he has his bearing. This was not magic, it was instrumental technology, a tool born from acute, generations-long observation of the natural world. It represents a profound scientific insight, the understanding that light itself carried hidden information that could be decoded with the right key. They identified a specific optical property in a specific mineral and developed a repeatable, practical method to exploit it for a critical purpose. This sunstone, coupled with their knowledge of seabirds, wave patterns, and star positions, formed a robust navigation system. It was this system that enabled the daring transatlantic voyages to places like Vinland, centuries before Columbus relied on more traditional celestial tools. The Viking Sunstone reveals a mindset that saw the environment not as an obstacle, but as a complex system full of solvable puzzles. It was a mindset that extended from reading the polarized sky to shaping the very structure of daily life and community. The Viking Sunstone was a tool for navigating uncertainty, but some ancient builders sought to create monuments of absolute certainty, structures meant to endure for the ages. The Romans achieved this not through magic, but through a revolutionary mastery of materials. While they did not invent concrete, they transformed it into a technological marvel, a substance so advanced that many of their structures still stand strong after 2,000 years, while modern counterparts often show significant wear after mere decades. This longevity is not a happy accident. It is the result of a sophisticated empirical science of materials. The secret, lost for centuries and only recently rediscovered by modern researchers, lies in a specific recipe. Roman engineers mixed lime with volcanic ash known as pozzolana and often used seawater in the process. When combined, this mixture triggers a slow, rare chemical reaction. Over centuries, minerals like aluminous tobamorite crystallize within the material's matrix. Unlike modern concrete, which weakens as it cracks and erodes, Roman concrete actually repairs and strengthens itself over time as these interlocking minerals grow, filling tiny fissures and creating a denser, more resilient whole. This was deliberate innovation. Figures like the engineer Vitruvius left detailed writings specifying exact ratios of sand, ash, and lime for different purposes, whether for a foundation, a wall, or, most impressively, for underwater construction. The harbor at Caesarea Maritima, for example, required concrete that could set and cure submerged, a challenge that would stump many builders even today. The Romans developed a formula that did just that, creating massive breakwaters that withstood the relentless Mediterranean waves. This points to a culture of systematic testing and refinement. They were not just following tradition, they were experimenting with different aggregates, observing long-term performance, and documenting their results to improve the next project. It represents a relentless pursuit of improvement through trial, observation, and record-keeping, the very hallmarks of an applied scientific mindset. Their infrastructural genius, from aqueducts that spanned valleys to domes that seemed to defy gravity, was built upon this foundational commitment to material science. It prompts a final consideration: if they could engineer substances to last millennia, how did they engineer their understanding of time itself, the ultimate framework for all their plans and monuments? Deep within the Temple of Hathor at Dendera, a stone carving has ignited a modern debate as electric as the phenomenon it is said to portray. The relief shows a large, elongated object resembling a glass bulb, inside which a snake stretches toward a socket held by a priest. A pillar supports the scene, and a figure stands nearby with what looks like an insulated cable. To some, this is unmistakable evidence of ancient Egyptian electric lighting, a literal interpretation that has fueled countless speculative theories. Mainstream Egyptology, however, offers a different, richly symbolic reading. The object is not a bulb, but a stylized lotus flower, the snake within representing a divine serpent emerging from the primordial waters, a classic motif of creation and rebirth. The so-called cable is a lotus stem, and the supporting pillar is the jed, a symbol of stability. This is not an electrical diagram, but a theological one, carved in stone to convey complex spiritual ideas. The enduring power of the light bulb interpretation, despite its likely inaccuracy, is profoundly revealing. It speaks to our own awe at Egyptian technical prowess. Their achievements in engineering and mathematics were so precise, so monumental, that they feel almost out of place in time, leading us to search for modern explanations. The Great Pyramid's alignment to true north with a margin of error of just 1/15 of a degree, the leveling of its 13-acre base to within an inch, these feats required a mastery of surveying, astronomy, and applied geometry that remains breathtaking. The Dendera relief becomes a kind of Rorschach test. Our desire to see a light bulb in it is, in a way, a tribute. It is our subconscious acknowledging that the minds capable of orchestrating the pyramid's construction must have possessed a form of knowledge that maps imperfectly onto our own historical categories. This pushes us toward a more nuanced understanding of ancient science. True innovation is not always about inventing the light bulb. It is about developing the cognitive frameworks that make such invention possible. The Egyptians excelled at abstract symbolic thought and systematic problem solving on a colossal scale. They could conceive of a project spanning generations, calculate the necessary angles and volumes without modern notation, and mobilize a society to execute it with flawless precision. That is a different kind of brilliance, one rooted in a deep, holistic understanding of order, measurement, and cosmic harmony. The real illumination at Dendera is not from a hypothetical ancient lamp, but from the enduring light of human ingenuity, expressed here not through circuitry, but through stone, symbol, and staggering ambition. This symbolic language of power and cosmic order finds a startling parallel in a much smaller, yet infinitely more personal, artifact from a different empire entirely. The same drive for precision that shaped stone and charted stars was also directed inward, toward the most complex system of all, the human body. While the Romans were mastering concrete, their medical practitioners were perfecting tools of a far more delicate nature. Archaeologists have uncovered Roman surgical kits containing an array of instruments that would look familiar in a modern sterilized tray: bronze scalpels with razor-sharp, replaceable blades, finely toothed bone saws for amputations, and slender probes and forceps for intricate work. The most telling tools, however, are the trephination drills designed to bore a small, precise hole in the skull to relieve pressure from a head injury. This was not a frantic act of desperation, but a calculated procedure performed with a tool engineered to prevent plunging too deep and damaging the brain. The existence of such specialized equipment speaks volumes. It implies a developed understanding of human anatomy, likely gained through observation of wounds and possibly even systematic study, a practice of medicine based on observable cause and effect rather than ritual alone. This clinical mindset flourished even more spectacularly in another ancient civilization. In India, the Sushruta Samhita, a medical text compiled around 600 years before the Common Era, describes procedures of astonishing complexity. It details over 120 different surgical instruments, many specifically designed for reconstructive surgery. The text provides step-by-step instructions for rhinoplasty, reconstructing a nose using skin grafted from the cheek, and for the removal of cataracts using a slender, curved needle to displace the clouded lens. These were not vague theories. They were precise, repeatable techniques taught to students who practiced first on fruits and clay models before ever touching a patient. This represents a monumental leap in thought, a move from generalized healing toward specialized, evidence-based intervention. It acknowledges that different ailments require different, tailored solutions, and that skill is built through rigorous training and accumulated knowledge. The ancient surgeon, whether in Rome or India, approached the body as a system to be understood and repaired, a mindset grounded in observation, classification, and refined technique. This was a healing art deeply connected to the tangible world, a philosophy that sought to mend the physical form with the same thoughtful care that an engineer applied to a wall or a navigator to his course. And just as these healers sought to restore the human form, other ancient minds sought to capture its essence, not with steel, but with pigment and perception. The surgeon's scalpel and the engineer's trowel both sought to manipulate the visible world, but one Roman artifact reveals a mastery of matter on a scale invisible to the human eye. In the quiet light of the British Museum, a cup from the 4th century holds a secret that flickers between two worlds. Known as the Lycurgus Cup, it depicts a scene from myth, the Thracian king Lycurgus entangled by vines. In reflected light under the sun or a gallery lamp, the glass appears a solid, opaque jade green. But hold a light source behind it, let the rays pass through, and the entire vessel undergoes a magical transformation, glowing with a rich, translucent ruby red. For over 1,500 years, this dichroic effect was a beautiful mystery, a trick of light that seemed almost supernatural. The truth, uncovered only in the 1990s with the aid of powerful electron microscopes, is more astonishing than any myth. The Roman glassmakers had, whether by brilliant accident or ingenious design, infused the glass with a precise mixture of gold and silver dust. But this was not coarse glitter. The particles were unimaginably small, measuring between 50 and 100 nanometers in diameter. To grasp that scale, a single nanometer is 1/1,000,000th of a meter, about 100,000 times thinner than a human hair. At this microscopic level, the particles of metal behave not as solid flecks, but in a way that interacts directly with light itself. When light hits the cup from the front, the nanoparticles scatter the green wavelengths, giving the glass its jade hue. When light shines from behind, passing through the matrix, the particles allow the red wavelengths to transmit, creating that luminous crimson glow. This is not a simple pigment, it is nanotechnology, a precise engineering of material at the atomic level to produce a predictable optical phenomenon. The most compelling question is one of intent. Did a Roman artisan, using perhaps a contaminated batch of materials or a particular combination of metal oxides, first stumble upon this stunning effect by pure chance? Almost certainly, but the Lycurgus Cup is not a unique fluke. Other fragments of Roman dichroic glass exist, indicating the effect was reproduced. This moves the story from accident to artistry. It suggests that once this marvelous property was observed, these master craftsmen began a process of empirical refinement. They would have experimented tirelessly, noting which mineral additives, which furnace temperatures, and which cooling processes yielded the most vibrant and consistent color change. They developed a recipe, a repeatable formula passed down through workshops, even if they had no scientific vocabulary for nanoparticles or light scattering. They knew the cause, the specific mixture, and they mastered the effect, the stunning visual transformation. This represents a pinnacle of ancient material science, a hands-on, trial-and-error exploration that achieved a result modern science would struggle to explain for centuries. It is a testament to the power of keen observation married to relentless experimentation. The cup is a physical paradox, a massive, handheld object whose true secret exists in a realm far too small for its makers to ever see, proving that the quest to shape our world has always reached beyond the limits of our senses. The desert plateau of Nazca holds a secret written not on parchment, but on the earth itself, a secret so vast it can only be fully comprehended from the heavens. Scattered across nearly 200 square miles of the arid Peruvian coastal plain are hundreds of immense geoglyphs, lines and shapes etched into the dark surface gravel to reveal the lighter soil beneath. From the ground, they appear as shallow, meandering pathways, but from the air, they resolve into staggering forms. A hummingbird with a wingspan wider than a jumbo jet, a spider with legs perfectly proportioned, a spiral-tailed monkey, and precise geometric shapes stretching for miles. For nearly 2,000 years, these lines have posed one of archaeology's most captivating questions. Why would a people who had no means of flight create art meant to be seen from a perspective they could never physically achieve? The answer may lie not in art for art's sake, but in a profound, functional relationship with their environment. One compelling theory views the Nazca Lines as a colossal astronomical calendar. Researchers like Maria Rai dedicated their lives to mapping the glyphs and found that many lines point directly to the position of the sun on the horizon during the solstices and equinoxes, while others align with significant star clusters. In a landscape with few permanent landmarks, these precise alignments could have served as a giant, fixed observatory, marking the critical turning points of the agricultural year, telling the community when to plant, when to harvest, when to expect the life-giving rains. But the connection to survival goes deeper into the earth itself. Another powerful theory links the lines to water. The Nazca region is one of the driest places on Earth, yet beneath the parched surface runs a complex network of underground aquifers fed by distant mountain runoff. Astonishingly, many of the largest and most elaborate figures and the long, straight lines that radiate from central points are positioned directly above these hidden water sources. The shapes may have served as ritual maps, marking sacred spots where water, the ultimate source of life, could be accessed. The lines themselves, especially the long trapezoids and runways, could have acted as ceremonial pathways for processions to pray for water, or even as sophisticated wind traps, their orientation channeling the rare breezes to prevent the precious water-bearing soil from being swept away. The creation of these geoglyphs was itself an act of monumental applied science. Without the ability to view their work from above, the Nazca planners relied on an advanced understanding of geometry and scaling. They likely used a system of stakes and ropes to plot out small-scale models, then transferred those proportions to the gigantic final canvas with astonishing accuracy. This required a communal, sustained effort across generations, a shared vision rooted in a meticulous observation of celestial cycles and terrestrial hydrology. The Nazca Lines were not a message for gods or aliens. They were a dialogue with the cosmos and the earth, a tool for survival etched into the very skin of the desert. They transformed their entire world into a living instrument, one that measured time by the stars and located life by tracing the veins of water hidden deep below. This mastery of earthly and celestial mapping leads us to wonder, how did other cultures master the ultimate map, the map of time itself? While the Nazca transformed their desert into a map of celestial and earthly cycles, the Maya of Mesoamerica built a map of time itself, an intellectual architecture of breathtaking scale and precision. Their calendar system was not a single tool, but an entire framework for understanding reality, a complex machine of interlocking gears made from numbers and observations rather than bronze. At its heart were three primary cycles working in concert: the Tzolk'in, a 260-day sacred calendar, meshed with the Hob, a 365-day solar year. But to track longer periods, they developed the long count, a linear tally of days that could pinpoint a unique date across thousands of years. This was not just for marking seasons, it was for aligning human events with the perceived rhythms of the gods and the cosmos. The true testament to their scientific mindset, however, lies in the astronomical accuracy they achieved within this system. Centuries of naked-eye observation, meticulously recorded in bark paper books called codices, yielded predictions of extraordinary detail. The Dresden Codex contains tables that accurately forecast solar eclipses and track the 584-day synodic period of Venus with an error of just 1 day in 500 years. To achieve this, Maya mathematicians made a conceptual leap that would revolutionize calculation: the use of a placeholder akin to zero, represented by a shell glyph, which allowed for elegant positional notation and the manipulation of large numbers. Their calendar was, in essence, a predictive cosmological model. It allowed priests and astronomers to anticipate celestial events, to plan rituals, and to understand their place within a vast, ordered universe. This represents a quantitative, pattern-seeking approach to nature that is a fundamental pillar of scientific thought. They observed, they measured, they recorded, and they computed to generate testable predictions about the world around them. This intellectual architecture of stone and star did not exist in isolation. It required a physical platform from which to watch the heavens. The Maya calendar wove a tapestry of time from the threads of mathematics and astronomy, but long before their civilization rose, another culture was etching its understanding of the cosmos directly into the landscape with stones that weighed more than houses. On the windswept Salisbury Plain in England, the great stone circle of Stonehenge stands as a silent testament to a prehistoric scientific endeavor. Its most famous alignment is undeniable as the sun rises on the summer solstice. Its rays pierce the heart of the monument, shining directly through a key archway framed by the massive sarsen stones. This was no accident but a deliberate, hard-won achievement. The true genius of Stonehenge, however, may lie in its complexity as a predictive machine. Some researchers propose that the arrangement of its 56 Aubrey holes, the circular pits that ring the site, could have been used as a primitive eclipse predictor. By moving markers around this circle in a specific pattern, generations of keepers might have tracked the cycles of the moon to forecast when its shadow would fall upon the earth. This suggests a purpose far beyond a simple solar calendar. It hints at a deep, long-term study of celestial mechanics. Stonehenge is not alone in this ancient sky-watching tradition. Across the Irish Sea, the massive Neolithic tomb of Newgrange, older than the pyramids, features a narrow roof box above its entrance. For just a few minutes at dawn around the winter solstice, a beam of sunlight travels down this long, dark passageway to illuminate the inner chamber, a dramatic annual event that must have held profound significance. On the Mediterranean island of Malta, the Mnajdra temple complex is precisely oriented so that the equinox sunrise lights up its main axis, while the solstice sunbeams align with the edges of megalithic doorways. These sites, separated by vast distances, share a common intellectual foundation. They required generations of patient, precise observation, the development of standardized units of measurement to plan such large-scale constructions, and the sheer engineering skill to translate abstract celestial patterns into permanent, monumental architecture. This was science as a communal, intergenerational project. It demanded a society capable of organizing labor, preserving knowledge across centuries, and investing immense resources into a structure with no practical shelter or defensive purpose. Its value was entirely conceptual, aimed at harmonizing human activity, agriculture, ritual, and community life with the immutable cycles of nature. These stone observatories represent a powerful, tangible interface with the cosmos, a place where empirical data, the recorded movement of sun and stars, blended seamlessly with spiritual significance. They are a physical form of a question: how do we find our place in the grand rhythm of the universe? The answer was carved in stone, aligned with light. And just as these builders learned to read the silent language of the stars, other ancient cultures discovered how to shape an invisible force that surrounds us all, the energy of sound itself. The stones of Stonehenge captured light, but other ancient builders learned to sculpt something equally intangible: sound itself. In the great theater of Epidaurus in Greece, a performer standing on the stage can drop a coin or speak in a hushed whisper, and the sound will travel with perfect clarity to the very last row of seats, over 100 feet away. For centuries, this was celebrated as a marvelous accident of design, a happy coincidence of architecture. Modern acoustic science, however, reveals a far more deliberate genius. The stepped limestone seats are not merely bleachers, they function as a sophisticated acoustic filter. Their precise curvature and porous material naturally absorb the low-frequency rumble of a moving, murmuring crowd, while simultaneously reflecting and channeling the higher frequencies of the human voice directly upward. This creates a stunningly clear auditory channel, a natural amplification system built from geometry and material choice. It was an empirical solution to a fundamental human need, ensuring that every word of a sacred hymn or a dramatic monologue could reach every member of a vast audience, uniting them in a shared experience. This intuitive mastery of sound wave propagation finds an even more mysterious expression deep underground. On the island of Malta, the Hal Saflieni Hypogeum, a labyrinthine subterranean temple carved from solid limestone around 5,000 years ago, possesses a remarkable acoustic property. Certain chambers resonate at specific low frequencies, around 110 Hz, a tone that falls within the range of a deep male voice. When someone chants or speaks at that resonant frequency within the space, the sound is amplified and distorted, vibrating through the very stone in a way that can be felt in the bones as much as heard. Researchers suggest this was not an architectural flaw, but a feature, a deliberate tool for creating an overwhelming sensory experience during rituals, perhaps to induce altered states of awareness or to simulate a powerful, disembodied voice. Whether under the open sky of Greece or in the enclosed darkness of Malta, these builders were engaging in a profound form of applied physics. They were manipulating the physical environment through trial and observation to achieve a precise sensory outcome, shaping space to conduct the human voice and the human spirit. This deep engagement with the properties of the natural world extended from the waves of sound to the far more tangible and relentless waves of the sea. While ancient theaters shaped the flow of sound, the desert demanded mastery over a far more precious flow, that of water itself. In the heart of the arid Persian plateau, where surface rivers were rare and the sun relentless, engineers devised one of history's most elegant and enduring feats of hydraulic ingenuity, the Qanat. This was not a simple well or an open canal vulnerable to evaporation. It was a subterranean river meticulously crafted by human hands. The process began with locating a water table at the foothills of a mountain range, often many miles from where the water was needed. From this mother well, skilled surveyors would plot a gently sloping underground channel, tunneling backward toward the settlement or farmland. The gradient was everything, a precise calculation achieved without modern instruments. It had to be steep enough to allow gravity to pull the water steadily forward, yet shallow enough to prevent erosion from collapsing the tunnel or creating destructive torrents. For every mile of this dark, hand-excavated channel, a series of vertical shafts were dug down from the surface at regular intervals. These shafts served a triple purpose. They provided ventilation for the workers below. They were used to lift out excavated soil and rock, and once the Qanat was operational, they became vital access points for maintenance and cleaning for centuries to come. The result was a self-sustaining, gravity-fed water supply that emerged cool and clean at the surface outlet, often flowing into a network of channels that fed gardens, farms, and public baths. This was systems thinking carved into the earth. It required a holistic understanding of geology to find the water, of physics to calculate the slope, and of sociology to organize the communal labor and legal frameworks needed for its upkeep. A single Qanat could stretch for dozens of miles and provide for an entire city, transforming barren land into lush, productive oases. These were not quick fixes, but generational investments in survival, infrastructure projects so resilient that thousands of them remain in use across Iran and the wider region today. The Qanat stands as a monument to environmental harmony, a technology that worked with the landscape rather than against it, tapping aquifers at a sustainable rate. It represents a philosophy of engineering where the goal was not to conquer nature, but to collaborate with its hidden logic, creating a legacy of life in the desert that flowed quietly for millennia. This grand, communal architecture of survival offers a striking contrast to our next artifact, a tool of such intimate and personal precision that it seems to speak of a completely different world. The Desert Qanat was a grand, communal answer to a slow and relentless crisis, but another ancient mind sought to detect a disaster that arrived in an instant without warning. In the year 132 of the Common Era, at the Han Dynasty court, the polymath Zhang Heng presented an object of both artistic beauty and profound purpose. Known as the Hufeng Didongyi, or instrument for measuring the seasonal winds and the movements of the earth, it was an ornate bronze vessel, perhaps as tall as a man. Around its circumference stood 8 dragons, each gazing outward with a bronze ball held delicately in its jaws. Below each dragon sat a corresponding bronze frog, its mouth open in anticipation. The elegance of its form, however, concealed a brilliant mechanical insight. Inside the vessel, historical accounts suggest, was a carefully balanced inverted pendulum. When seismic waves from a distant earthquake reached the instrument, even from hundreds of miles away, the subtle shaking would disturb this precise internal mechanism. The motion would trigger just one of the 8 dragons to release its ball, which would clatter into the mouth of the waiting frog below. The direction of the fallen ball indicated the compass bearing from which the tremor had originated. This was not magic, it was an early form of inertial seismoscope, a device designed to translate an invisible, terrifying force of nature into a clear, actionable signal. The genius of Zhang Heng's device lies in its conceptual leap. He moved beyond the experience of the quake itself, the chaos, the fear, the destruction, and sought to measure it. He aimed to collect data, to turn a subjective event into an objective directional reading. This shift from enduring a disaster to systematically observing it is a foundational pillar of the scientific mindset. It represents a desire to impose order on chaos through understanding, to find a pattern in the violence of the earth itself. While the exact internal mechanics have been lost to time, modern engineers have created working reconstructions based on the principles described, proving that the device was not merely ceremonial but functional. It stands as a testament to a mind that saw the world as a system of forces waiting to be decoded, and it prompts a quieter, more fundamental question. If we can build instruments to measure the shaking of the ground, can we also build tools to measure the abstract realm of thought and quantity itself? The dragon's bronze ball fell with a clear, directional clang, translating chaos into data. Yet the human desire to quantify the world stretches back far beyond ornate instruments, to a time when the tool itself was a humble bone. Along the shores of Lake Edward in the Congo, a small artifact was unearthed that quietly rewrites the timeline of human thought. The Ishango Bone, a baboon's leg bone dating back over 20,000 years, carries a series of deliberate notches carved in distinct grouped columns. At first glance, it could be a simple hunter's tally, but the arrangement of these marks suggests something far more sophisticated. One column groups notches in sequences that mirror prime numbers, another shows a clear pattern of doubling. Some researchers see in these groupings a record of lunar phases, a 6-month calendar etched into bone. Others interpret it as an early multiplication table or a tool for basic arithmetic. Regardless of its precise purpose, its meaning is monumental. This is not a tool for hunting or building, but a tool for thinking. The Ishango Bone represents the externalization of memory, the birth of recorded mathematics. Someone in the deep Upper Paleolithic era was not just experiencing the world, but actively seeking to map its underlying numerical order. They observed a pattern in the cycles of the moon or in the grouping of objects, and they devised a system to capture that pattern, to hold it in their hands and share it across time. This act of carving notches is the primal seed of all scientific measurement. It is the moment counting became more than an instinct, it became a recorded language. The bone is a fossilized thought, proving that the drive to find logic in nature, to reduce the flux of experience to manageable, repeatable quantities, is an ancient and fundamental part of our identity. From this intimate, personal tally stick used by a single individual to track time or trade, we leap forward to an artifact that speaks of a society engaged in a vastly more complex form of calculation, one that measured not just quantities, but the very structure of human relationships and cosmic order. The Ishango Bone captured private thought in a series of notches, but on the sun-drenched island of Crete, another artifact hints at a desire to communicate ideas outward, in a format meant to be shared. Discovered in the Minoan Palace of Phaistos around 1908, the Phaistos Disc is a small, fired clay tablet, roughly the size of a common dinner plate. Its surface is not inscribed by hand, but covered on both sides with a spiral of mysterious symbols, stamped into the soft clay with individual seals before it was baked. There are 241 impressions in total, comprising 45 distinct signs, ranging from human figures and birds to shields and flowers, all arranged in clear groups. For over a century, this beautiful object has resisted all attempts at translation, its language and message completely lost, yet its very form speaks volumes about the mind that created it. The use of pre-formed stamps is the critical clue. This was not a one-time artistic inscription. It implies the existence of a standardized set of symbols, a kind of primitive typeface, and an intention for reproduction. Someone or some group had developed a system of signs and a technology to replicate them consistently. Whether the disc recorded a religious hymn, a list of royal goods, the rules of a ritual game, or a historical treaty, its purpose was to structure information in a fixed, repeatable format. This is a cognitive leap of immense significance. It represents a move from ephemeral speech or unique carvings toward a technology of organized thought, a proto-linguistic tool for encoding meaning in a way that could be understood by others who knew the code. The Phaistos Disc is a fossilized system. It shows a culture grappling with the abstraction of ideas into symbols and the organization of those symbols into a deliberate sequence. It is a step, however enigmatic, on the long path toward the formal writing systems that would later codify everything from scientific principles to epic poetry. This drive to impose a systematic order on information finds a powerful parallel in a much grander ambition: the desire to impose a systematic order on the physical world itself, to structure not just symbols on clay, but the very space in which a society lived and governed. The systematic order of symbols on a clay disc finds its ultimate expression in the systematic order of an entire city. Far to the east of Crete, along the fertile floodplains of the Indus River, a civilization flourished with a vision of urban life so rational and planned it feels startlingly modern. The great city of Mohenjo-Daro, built around 2,500 years before the Common Era, was not a haphazard collection of huts and pathways. It was a masterpiece of premeditated design laid out on a near-perfect north-south, east-west grid system. Its streets were wide, straight, and intersected at right angles, creating uniform city blocks. This was not an organic growth pattern. It was the result of centralized, authoritative planning that required a shared, standardized unit of measurement to succeed. Every brick in Mohenjo-Daro, from the grand structures to the humblest home, adhered to a common ratio, its dimensions consistent across the entire city. This standardization speaks of a society that valued order, efficiency, and perhaps even a kind of civic equality in its fundamental building blocks. But the true genius of this urban plan lies beneath the streets. The city boasted one of the world's first sophisticated public sanitation systems. Houses were connected to a network of covered drains and chutes that carried waste away from living areas, channeling it into larger street-side sewers. These drains were designed with inspection holes and were built with a slight gradient to ensure flow, preventing stagnation. Public wells provided clean water at regular intervals, separating the supply from waste. This was applied science on a grand civic scale, a profound understanding of the link between public health, engineering, and social organization. The planners of Mohenjo-Daro were systems thinkers. They grasped the interplay between environment, infrastructure, and community well-being. Their grid was not just about efficient movement, it was about creating a sustainable, hygienic, and functional human habitat. They implemented abstract principles of geometry, hydraulics, and logistics to solve the practical problems of dense urban living, problems many cities would struggle with for millennia to come. This was a mindset that saw the city itself as a machine for living, each component, the brick, the drain, the well, the street, designed to work in harmony with the others. From this macroscopic view of a perfectly planned society, we shift our perspective to a realm of intimate, microscopic artistry, where the tools were not bricks and drains but fibers and dyes. The perfectly planned grid of Mohenjo-Daro reveals a society that mastered the macroscopic logic of community, but another ancient craft required a mastery of the microscopic, of manipulating materials at the very level of the thread. While the Indus Valley cities stand as monuments to public order, a different kind of artifact, one that is soft, fragile, and astonishingly long, preserves a different kind of order entirely, the order of events. Stretching an incredible 70 meters, the length of an Olympic swimming pool, the Bayeux Tapestry is not a tapestry at all, but an epic narrative embroidered in colored wool on linen cloth. Created in the 11th century, likely within a generation of the events it portrays, it chronicles the story of the Norman conquest of England, from a disputed oath to the climactic Battle of Hastings. It is a breathtaking feat of historical methodology stitched into being. This embroidered chronicle operates with a rigorous, consistent visual language. Borders frame the main narrative with symbolic animals and scenes from fables, while a running Latin inscription acts as a caption track. The figures themselves are depicted in a clear, sequential manner, their gestures and positions conveying alliances, betrayals, and pivotal moments with the clarity of a modern storyboard or documentary film. Consider its depiction of Halley's Comet, which streaked across the sky in 1066. The embroiderers did not treat it as a mere decorative flourish. They placed it prominently in the narrative sequence, showing awestruck observers pointing toward it, accurately recording a datable astronomical event and interpreting its cultural impact as an omen. This was systematic observation translated into a communication technology. In an era when literacy was limited to a privileged few, the tapestry was a tool for mass communication, a way to preserve and transmit a complex, politically charged history across barriers of language and social class. It could be unrolled and explained in a great hall, making the story accessible to all. This mindset of careful observation, sequential narrative, and meticulous recording is a foundational scientific and historical practice. The anonymous creators understood that knowledge is fragile, that it must be captured, organized, and transmitted with accuracy for it to endure. The Bayeux Tapestry is a cognitive tool, a physical manifestation of the human need to make sense of causality and consequence, to freeze the flow of time into a pattern that can be studied and understood by future generations. It represents the thread, both literal and metaphorical, that connects event to memory and memory to legacy. This profound drive to preserve knowledge finds its ultimate expression not in a single narrative cloth, but in a repository designed to hold the entire world's memory, a place where such threads of understanding are gathered and protected. The fragile threads of knowledge preserved in cloth and bone find their most ambitious home not in a single story, but in a collective dream made of papyrus and stone. On the shores of the Mediterranean, the Ptolemies of Egypt built something unprecedented, a tool for the mind itself. The great Library of Alexandria was not merely a building filled with scrolls, it was an engine for thought, a conscious attempt to aggregate the entire known world's understanding under one roof. Its mission was audacious: to acquire every book, to copy and translate works from across civilizations, from the geometry of Greece to the astronomy of Babylon and the medicine of the Indus. This was more than hoarding, it was a systematic project of categorization and critique. Scholars were paid not just to preserve texts, but to debate them, to compare conflicting accounts of history or natural philosophy, and to identify errors through logical analysis. The library created an environment where a physician could consult texts on botany, where an astronomer could be challenged by a mathematician, where the synthesis of different fields was not just possible but encouraged. In this sense, the library was the ultimate meta-tool, a cognitive instrument designed to accelerate the discovery of all other instruments. It recognized that knowledge grows not in isolation, but through the friction and fusion of ideas, through the collaborative, cumulative work of many minds across generations. The tragic fate of this institution, lost to the fires of conflict and time, is a haunting lesson in the fragility of human understanding. Yet its ideal endures as the very blueprint for the scientific mindset, a testament to the belief that to comprehend our world, we must first gather, organize, and fearlessly question everything we think we know. From this vast repository of aggregated wisdom, one specific cognitive tool emerges with particular power, a tool that translates the library's abstract ideal into a concrete guide for action, the map. The library's ambition was to contain all knowledge, but one scholar within its orbit sought to contain the world itself. In the 2nd century, Claudius Ptolemy compiled his Geographia, a work that did far more than present a single picture of the Earth. It was a manual for building reality, a set of instructions for creating a model of the known universe. Ptolemy knew the world was a sphere, a fact established by Greek thinkers centuries before. His great challenge was to translate that curved, three-dimensional truth onto the flat, two-dimensional surface of a papyrus scroll. His solution was a mathematical framework, a coordinate grid of latitudes and longitudes that could assign a unique numerical address to any location, from the Pillars of Hercules to the distant Silk Road. This was a leap from drawing what you thought you knew to calculating where things should be based on a system. He gathered every traveler's account, every merchant's log, every conflicting report of distances between cities, and he attempted to reconcile them all through a process of critical comparison and estimation. His resulting map was filled with errors. The Mediterranean was stretched too long, Asia extended too far, and a vast, unknown southern continent was hypothesized to balance the landmasses of the north. Yet the errors are not the point. The methodology is everything. Ptolemy was not illustrating folklore. He was constructing a testable, scalable model based on the best available evidence. He provided the mathematical tools so that future mapmakers, armed with better data, could correct his work and produce a more accurate picture. The Ptolemaic map was a tool for navigation in theory, but the Geographia itself was a profound tool for thought. It framed the world as a puzzle to be solved through measurement, logic, and the patient accumulation of data. It was an attempt to impose a rational, predictable order onto the messy, reported reality of human exploration. This drive to model physical space, to create a systematic representation of a complex system, finds a direct and powerful parallel in a very different kind of ancient endeavor, one that sought to model not geography, but the very structure of human society itself. The stele of Hammurabi stands taller than a man, carved from a single pillar of black diorite. At its top, a bas-relief shows the Babylonian king receiving the scepter of authority from the sun god Shamash. Below this divine endorsement, the stone's surface is covered from shoulder to base in meticulous cuneiform script, row upon row of wedge-shaped characters that detail not a conquest or a prayer, but a set of rules. This is the Code of Hammurabi, proclaimed around 1,750 years before the Common Era. It is far more than a simple list of punishments. It is a monumental tool of social engineering, one of humanity's earliest and most ambitious attempts to apply systematic, rational thought to the chaotic realm of human conflict. The king's stated purpose was clear: to cause justice to prevail in the land, to destroy the wicked and the evil, that the strong might not oppress the weak. To achieve this, he did not rely on the arbitrary judgments of local officials. Instead, he created a standardized system, a code of 282 laws that aimed to bring predictability to every corner of his diverse empire. The principle of lex talionis, often summarized as an eye for an eye, is its most famous feature, but this was not a call for blind vengeance. It was a principle of proportionality, an attempt to limit retaliation and make the punishment fit the crime in a measurable, consistent way. The code's true sophistication, however, lies in its granular categorization. It recognizes distinctions that any modern legal system would grapple with. It differentiates between intentional and accidental harm. If a builder's poorly constructed house collapses and kills the owner's son, the builder's own son is to be put to death, a stark linkage of consequence and responsibility. It accounts for social status with different penalties prescribed for offenses against a noble, a commoner, or a slave. It covers commerce, setting standards for wages, prices, and liabilities for merchants. It addresses family law, inheritance, and professional malpractice. This was an act of profound observation and classification. Hammurabi's scribes and officials had to observe the common conflicts of their society, analyze recurring problems, and then devise standardized solutions that could be applied from Babylon to the distant provinces. The code itself was a cognitive tool, a written framework designed to manage the escalating complexity of an urban, stratified civilization. It moved justice from the realm of memory and oral tradition into the realm of fixed, accessible text. Copies were likely displayed in temples across the empire, making the law a public, knowable entity. This represents a foundational moment in the history of social science. It is the mindset that seeks universal principles within human behavior and then builds a consistent system upon them. The stele is a fossilized thought process, one that says human interactions, like the movements of stars or the flow of water, can be understood, predicted, and regulated through rational order. It is governance treated as a solvable engineering problem. From this grand, external framework for governing a society, we turn inward to a discipline that sought to govern the self, not through law, but through the meticulous, lifelong practice of attention. The law codes of Hammurabi sought to order society from the outside, but another ancient discipline pursued order from within, turning the human being into its own laboratory. Across the Indian subcontinent, a system of profound introspection was being codified, one that approached the mind and body with the rigor of a scientific investigation. The Yoga Sutras of Patanjali, compiled over 2,000 years ago, are not a collection of myths or prayers, but a precise manual for a radical experiment, the experiment of the self. This text outlines an 8-limbed path, a structured methodology that moves from ethical precepts through physical postures, breath control, and stages of meditation toward a state of focused awareness. This was not vague spirituality, it was a systematic technology of consciousness. Each aspect of the practice, from the controlled breathing of pranayama to the sustained postures of asana, served as a tool for gathering data. The practitioner becomes both the scientist and the subject, formulating a kind of internal hypothesis. If I sit in this specific posture and regulate my breath in this counted pattern, what happens to my heartbeat, to the chatter of my thoughts, to my sense of equilibrium? The practice itself is the experiment, repeated daily under controlled conditions of time and environment. The observed outcomes are then meticulously noted, not in a lab notebook, but in the direct experience of the practitioner. Does the mind become more steady? Does a sense of agitation dissipate? Does physical endurance increase? This process of hypothesis, experimentation, and observation forms the core of an empirical science of introspection. The ancient yogis were mapping the interior landscape with the same dedication that a cartographer applied to a coastline. They identified specific techniques to influence the nervous system long before modern neurology had the tools to measure it. They understood, through relentless trial and observation, that the breath is a direct dial to the state of the mind, that certain physical alignments can alter energy and attention, and that consciousness itself can be trained and refined through disciplined repetition. This represents a breathtaking inversion of the scientific gaze. While the Babylonians looked outward to legislate human interaction, and the Romans looked outward to engineer their environment, the yogis turned the lens of inquiry inward. They asserted that the most immediate and mysterious territory for exploration is our own being. Their work stands as a monumental achievement in the history of human thought, proving that the drive for systematic understanding knows no boundary, not even the boundary of our own skin. This deep, internal science of self-mastery forms a perfect complement to our final exploration, which looks not inward at the individual, but outward at the collective power of a community to solve a problem of staggering scale. The yoga's inward focus cultivated individual awareness, but a different city turned its collective focus outward, toward the monumental challenge of governing itself. In the bustling agora of ancient Athens, amidst the philosophers and merchants, a radical social tool was being forged, one more complex than any lever or lens. This was Athenian democracy, a system engineered not from stone or bronze, but from procedure, speech, and human participation. Its core institutions, the General Assembly where thousands of citizens voted on laws, the popular courts with juries chosen by lot, and the use of sortition to fill many administrative posts, were designed as mechanisms for a single purpose: to process the city's problems through collective intelligence and public debate. This was an explicit experiment in distributed governance. By selecting ordinary citizens by lot for juries and councils, the system aimed to prevent power from concentrating in the hands of a wealthy or hereditary few, distributing the burden and privilege of judgment across the citizen body. The assembly itself was a furnace for rhetoric, where speakers had to persuade their peers not with force but with logos, with reasoned argument and evidence. Success depended on constructing a logical case that could withstand public scrutiny and counter-argument. While this system was deeply flawed by modern standards, excluding women, enslaved people, and foreigners, its internal logic was groundbreaking. It treated politics as a skill that could be systematized and a process that could be engineered for stability and fairness. Thinkers like Aristotle took this empirical approach even further. He did not just philosophize about the ideal state. He and his students collected and analyzed the constitutions of over 150 different Greek city-states. They compared their structures, their laws, and their historical outcomes, seeking patterns in what made a society thrive or descend into conflict. This was political science in its earliest, most systematic form, an attempt to derive principles of social organization from observable data. Athenian democracy, for all its exclusions, represents perhaps the most ambitious ancient tool of all, a large-scale technology for managing human society itself. It was a conscious attempt to channel the collective passions and intellect of a community into a machine for public problem-solving, using the tools of debate, procedure, and shared responsibility. It highlights an ancient quest that mirrors our own, the relentless drive to develop better methodologies for living together. As we have journeyed from intricate gears to vast city grids, from surgical scalpels to systems of justice, a unifying thread begins to pull taut, connecting every artifact and innovation we have explored. These scattered fragments of genius, from the gears of Greece to the grids of the Indus, are not isolated miracles. When we step back and view them together, a breathtaking pattern emerges across continents and millennia. Civilizations that never met, separated by vast oceans and mountain ranges, were independently converging on the same profound ways of thinking. They each learned to watch the world with meticulous patience, noting the dependable rhythm of the stars and the stubborn behavior of materials. They each invented systems of measurement, standardizing the cubit, the pace, or the brick, because they understood that to build anything lasting, you must first agree on a unit. They each mastered the art of translation, taking an abstract principle like leverage or polarized light, and giving it physical form in a lever or a sunstone. And crucially, they each developed methods to record what they learned, in cuneiform on clay, in stitches on linen, or in precise ratios for concrete, ensuring that knowledge could outlive its discoverer. This shared toolkit of the mind reveals something fundamental. What we see in these artifacts is not modern laboratory science, but its direct and powerful ancestor. It was driven by the very same impulses that fuel research today: a deep curiosity about how the world works, a practical desire to predict events and control outcomes, and an unwavering need to solve the problems right in front of them, whether that problem was irrigating a desert, navigating a trackless sea, or healing a grievous wound. These tools are evidence that the scientific mindset is not an invention of the Renaissance or the Enlightenment. It is a latent human capacity, a way of engaging with reality that lies dormant within us, waiting for the right conditions to awaken and flourish. It blooms in eras of relative stability, where resources allow for specialization, and where a culture values inquiry enough to support the tinkerer, the star watcher, and the record keeper. This perspective changes everything. It means that innovation is not a straight, upward line on a graph. It is a spiral where insights are discovered, forgotten, and rediscovered in new forms across ages. The genius of our ancestors was not lesser than our own. It was simply expressed in the materials and metaphors available to them. They engineered with society and stone as masterfully as we engineer with code and silicon. Their legacy is a powerful reminder that the drive to understand, to measure, and to build is woven into the very fabric of our species. It is a timeless conversation between the human mind and the mysteries of the universe, a conversation that continues in every laboratory, workshop, and curious glance at the night sky. This shared tapestry of ingenuity across time and culture shatters a persistent myth, the idea that human progress is a straight, unbroken line from primitive superstition to modern science. What we have witnessed is not a linear march, but a constellation of brilliance flaring up in different eras and places, each illuminating the same profound truth. These artifacts are far more than historical curiosities or lucky accidents. They are the physical evidence of a scientific mindset operating far ahead of its time, a mindset rooted in meticulous observation, fearless experimentation, and elegant, systematic problem-solving. The Antikythera maker calculating lunar cycles, the Roman artisan puzzling over nanoparticles in glass, the Inca engineer locking earthquake-proof stones, all were engaged in the same fundamental project: to decode the rules of their world and apply them with precision. This reveals that the drive to measure, to test, and to understand is not a modern invention, but a timeless strand woven into the very fabric of the human story. It is a capacity that lies dormant within us, waiting for the right conditions of stability, curiosity, and need to awaken. As we confront our own era's complex challenges, from environmental shifts to technological dilemmas, we can draw powerful inspiration from these ancient innovators. They did not have our tools, our databases, or our global networks. They worked with the materials and knowledge available in their age, whether it was bronze, stone, crystal, or clay, and with that they achieved the extraordinary. They looked at a problem, observed its patterns, and devised a solution that often lasted for millennia. Their legacy is a call to humility and to boldness. It asks us to look at the past not as a simple prelude to our own time, but as a rich repository of human cleverness, a source of wonder that can rekindle our own creative spark. Let it remind you that the future is not something that simply happens to us. It is something we build, question by question, experiment by experiment, just as they did. If this journey through ancient minds has shifted your perspective, we would love to hear your thoughts. Share this exploration with someone who sees the world with curiosity, and join us for more journeys into the mysteries that connect our past to our present.